Now let's consider a situation involving a collision. So we have the sport of curling. Large stone slides along the ice, hits another large stone. Shooter throws the initial stone, sliding it along the ice. Has a mass of 18.9 kilograms traveling at 1.5 meters per second. So we're going to have a lot of given information here. So let's start diagramming and identifying. So here is our first stone. And it has a mass of 18.9 kilograms. And it is traveling at 1.5 meters per second. It collides with a second stone. Second stone, I'm going to draw in here. Mass of 19.1 kilograms. That is initially at rest. They collide. So we'll put a kind of a division there. After the collision, the second stone moves forward at 0.95 meters per second. So here's our second stone, 0.95 meters per second. The first stone, it is moving after the collision, but we don't know how fast it's moving. So that's what we want to calculate in part A. You have a situation with a collision, and in a collision, the objects push on each other. That means that's an internal force, and in internal forces, momentum is conserved. And so I can go on part A, Pi is equal to Pf. So then object 1 and object 2, the momentum before, object 1 and object 2, the momentum after. So then mv1 plus mv2 before the collision equals mv1 plus mv2 after the collision. Now, everything has momentum except for object 1 before the collision. We're going to end up with a 0 there. But everything else has momentum, and what we're after solving for is the velocity of object 1 after the collision. So filling in values, 18.9 kilograms multiplied by the 1.5 meters per second plus 0. Afterwards, you've got 18.9 kilograms times the unknown velocity plus 19.1 kilograms multiplied by the 0.95 meters per second. Do your algebra, solve down for V1. We get that velocity just after the collision to be positive 0.54 meters per second. And the positive means forward. Now, if we had had multiple objects moving in opposite directions, we would have had to represent one of those velocities as negative. But for this one, everything is moving in one direction. Part B. Calculate the change in kinetic energy that occurs during the collision. So then, before the collision and after the collision, we want to compare the kinetic energies. So then change in kinetic energy, that would be final minus initial. Well, more specifically then, we've got final. That would be a 1/2 mv squared for object 1 and a 1/2 mv squared for object 2 minus the initial. Well, object 2 is not moving initially, but object 1 is. So then 1/2 mv1 squared, and then 0 for object 2. And then let's fill in all our values. So 1, and this is final, and this is initial. So object 1 final, that would be here. So this is 1/2 times 18.9 kilograms times the velocity we calculated here, 0.54 meters per second squared. Object 2 final, which would be here. This is 1/2 times 19.1 meters per second. 19.1 kilograms. times the 0.95 meters per second, and that's squared. So that's all of the final, minus the initial 1/2 times the 18.9 kilograms multiplied by the 1.5 meters per second, quantity squared, and then the 0. So then when we calculate there, we end up with 9.89 joules of energy that are dissipated. So it's very important in conservation of momentum or collision problems that you organize your information, especially with a diagram, because you have so much given information. Ponder physics.